Hey everyone. In this video, I will be reviewing Chapter 4, which is on probability. So Section 4.1 is on sample spaces and probability. And what are the important things that you really want to take away from this section? Well, number one, let's talk about a couple definitions. Number one, a probability experiment is a chance process that leads to well-defined results called outcomes. So it could be, maybe rolling a die, or flipping a coin, picking a random card. Okay, and the sample space of a probability experiment it's the set of all possible outcomes in a probability experiment. So in rolling the die, I guess, um, I don't want to put it here just yet, but for example, in the rolling the die example, the sample space would be 1, 2, 3, 4, 5, 6, right? Because that's every possible outcome when you're rolling a die. What would the sample space be for flipping a coin? Well, that would be heads and tails, right? Those are the only two outcomes, so that would be the sample space. Picking a random card, so say you have a random deck of cards which has 52 cards in it. We'll talk about that later. Not everybody's familiar with cards, of course, but since there's 52 cards in a deck, there would be 52 outcomes for that probability experiment if you were to just pick one randomly. So very important, sample space. Very, very, for probability, sample space is extremely important. So let's look at some examples, I guess. Sure. So I guess we could look at the ones above. I already mentioned, well, I already said those. Let's do a new one. Find the sample space for rolling 2 dice. Okay, and if perhaps you don't know what a dice, what a die is, it has 6 sides. And they're 1, 2, 3, 4, 5, and 6. So what are every possible outcome? Well, one outcome is we get a 1 on the first die, a 1 on the second die. we're not talking about the sum. That would be a different thing. We also can get a 2 on the first die and a 1 on the second die. A 3 on the first die, a 1 on the second die. A good way to think about sample spaces when two things are happening in a kind of a compound event, which is what's going on here, because you roll not one die, but two. When it's two dimensions, it's good to do a graph, a table of outcomes. Unless, of course, there's a very, very large amount of outcomes, in which case you won't want to list them all. You'll want some other way of figuring out how many ways there are. But here we're just looking for the sample space. So here's the die. We could get a 1, a 2, a 3, a 4, a 5, or a 6 on the first die, for example. And then we'll put the second die here. You could get a 1, a 2, a 3, a 4, a 5, and a 6. So the sample space would be, 1, 1, for example. 1, 2. 1, 3. 1, 4. 1, 5. 1, 6. Let me pause for a sec while I write them all down so I don't waste your time here. Okay, and so here would be our sample space, which it looks like to me there's 36 different possible outcomes. Let's look at another one. Find the sample space. Find the sample space. For the gender of the children, if a family has 3 children. Okay, well, if they're having 3 kids, think about what are all the outcomes. And sample space is usually written as a set, which is curly braces, and then that's when you list where you list every outcome. So if they're having 3 kids, right, maybe one outcome is all of them are boys, right? So BBB. Perhaps we have another one, boy, boy, girl, boy, girl, boy, girl, boy, boy. So I'm kind of doing this systematically, where first I listed the entry that has 3 boys. Now I'm listing the entries that have 2 boys. Then I'll list the entries that have 1 boy and then have 0 boys. Because when listing things in a sample space, you want to go in some sort of systematic way, because it's a lot less likely to mess up by repeating the same outcome or missing an outcome or something like that. So now I'll do a single boy. So boy, girl, 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 boy, girl, and girl, girl, boy. My G's are looking like 6s now. And then girl, girl, girl. That would be the ones with 0 boys. And that would be the sample space in this case. So when there's more than 2 possibilities in a probability experiment like this, there were in the first example we did where we're rolling 2 die, that's 2 events. And for 2 events, it's good to draw a graph like this. But for 3 or more events, like in this one, where we're looking at what happens, the probability of the gender when it's 3 kids, so that's more than 2 events. In that case, it can also be really helpful to use a tree diagram. So can also use a tree diagram to help map outcomes when there are more than 2 events involved. And so let's go ahead and do the same example, but let's use a tree diagram to show you guys how to do that. So the number of outcomes, I'm sorry, the number of events, you kind of list them as columns, and then you list every possibility starting from left to right. So for the first kid, well, what are all the outcomes for the first kid? Well, it could either be a boy or a girl. And then assuming that we've got a boy as the first kid, what could be the second kid be? Well, again, a boy or a girl. So we're going to draw from the first outcome here the next two outcomes. And if the first kid was a girl, what could the second two be? Again, a boy or a girl. We do the same thing one more time, kind of extrapolating here. And then you look at each path from left to right possible, and that gives you an outcome. So tracing the trees this way gives an outcome. That's boy, boy, boy. Then I'll do the next one. So the next possible outcome would be BBG. You just kind of go down the list. The next one will be BGB. And then BGG. Here we've got GBB, GBG, GGB, and GGG, which is a good way when, again, I said when there's more than two events happening in a question. Okay, so that allows us to start talking about what's called classical probability. It's an extremely easy formula. Let's go ahead and give the definition. So the probability of any event E is, so it's the total number of outcomes. I'm sorry, scratch that. It's the number of outcomes that that event occurs in over the total number of outcomes. In the whole sample space. So that's why it's really important to be able to come up with the sample space, because it's the denominator of our probability formula. Let me just move this over a little. Okay, it's the number of outcomes in E over the total number of outcomes in the sample space. It could be denoted like this as well. P of E, which means the probability of E occurring, is equal to N of E over N of S. Where N of E is the number of elements in E. Or I'll just say E, or I guess we just need to know S is, where S is the sample size. Or sample space, sorry. And that N just means number of elements in. And so rounding is always, or very usually, so probability, rather. So probability is usually a fraction. or I guess you can always view it in the form of a fraction. But it's going to be between 0 and 1. Where 0 means it's never going to happen, and 1 means it's always going to happen. So if I said when rolling a die, what's the probability of getting a number bigger than 0? Well, every number on a die is bigger than 0. So the probability of that happening would be 1 or 100%, right? To put it to percentage, you just move the decimal 2 spots to the right. And if I said, what's the odds of rolling a 20 on a 6-sided die? Well, that's impossible. That will never happen. So the probability of that would be 0. But you really need to remember this. It's the number of outcomes, the number of favorable outcomes, another way of thinking it, over the total number of outcomes. That's often what I say, favorable over total. So let's ask some questions. Find the probability of getting a red 8 when one card is randomly selected. From an ordinary deck. Let me get a picture of a deck of cards real quick. Okay, so I've got a deck of cards here. A deck of cards is a really good it's a really good set of things to talk about in a probability experiment. The sample space is pretty big and diverse. There's a lot of differences amongst the cards, but also a lot of similarities. So you could ask a lot of good questions. If you don't know much about cards, these are what are called their suit. And these are the clubs, the spades, the hearts, and the diamonds. Often they also talk about face cards. So if you don't know what the face cards are, it's these ones over here on the right. The jacks, queens, and kings. The ace is not a face card. Only the ones that have a literal face, like the jack, queen, and king. So they do ask a lot of questions like that in the book. So just trying to explain that here, in case you're not very aware of cards. Okay, and so remember, what is our formula for probability of an event? It's favorable over total. What's our event here? It says we're looking for the probability of getting a red 8. A red 8. So that's our event. That's essentially what E is, right? Probability of an event occurring. And instead of E, I'll just say red 8. So probability of a red 8 is equal to. And what's it going to be? Favorable over total. So how many of the outcomes are favorable to our event of getting a red 8? And what's the total number of events in the entire sample space? It's the fraction of that. Well, there's 2 red 8s, right? The 8 of hearts and the 8 of diamonds. In case there are any colorblind people watching this, these are the black cards up here, and these are the red cards. And so there's 2 red cards, the 2 red 8s. the 8 of hearts and the 8 of diamonds. So we end up getting 2 over the total number of outcomes. Well, there's 52 possible outcomes out of 52. So that gives us, it reduces to 1 over 26, which is what is a decimal. That's how you find the percentage probability. It's 0.03846. Which you can view as a percentage by, remember, moving the decimal 2 spots to the right. That'd be 3.846%. That would be your probability of getting a red 8. Okay, so there's a lot of good questions on those. Remember, the probability of an event can only be between 0 and 1. Can't be bigger than 1. That's not possible, right? Because your numerator can't be bigger than your denominator, because the denominator is the number of elements in the sample space. Well, if your numerator is bigger than the number of elements in the sample space, you just haven't included everything in the sample space that you're supposed to. So the highest it could ever be is 1, and it can't be negative. You could have 0 in the numerator, but you can't be negative, so the lowest it could be is 0. Okay, and so that's classical probability, basically probability theory, probability in theory, what would happen. That's what's called classical probability. Another type of probability is called empirical probability. It's not talking about what happens in theory, but actually, rather, it talks about what happens in practice. So it's empirical probability is essentially talking about an experiment of some sort. So say you survey. Well, rather, let me put a short definition here. Empirical probability is about it's an observed probability. Okay, and so, say you did some sort of experiment. Say you viewed the first 20 people's choice of donut. And you come up with some sort of frequency distribution of all the outcomes. So let's say you've got our flavor over here. And the frequency that they chose that. So how many times they chose that. And let's just say they only pick one donut. So let's say there's glazed, chocolate, I'll just say sprinkles, and strawberry, sure, why not? And we noticed that 5 people got glazed, 2 got chocolate, 4 got sprinkles, and 9 got strawberry. All right, as you may notice here that the sum of the frequencies has to add up the number in the sample, and it does here. If you add these up, it is 20. And we could then maybe say, find the empirical probability based on this study or experiment that a random person will choose sprinkles. Well, the formula for empirical probability, it's pretty much the same. They've got a typo here in the book, so I don't want to use their definition. But it's really just the frequency over the total number of observations. So it's pretty much the same formula, just favorable over total. So the probability that somebody chose sprinkles, out of the 20, how many of those 20 choices are favorable to somebody picking sprinkles? Well, that's 4. And what's the total number of outcomes that we observed? Well, 20. So we end up getting 4 over 20, which is 1/5, aka 20%, right? 0.2 or 20%. And that's pretty much empirical probability. It's talking about some sort of experiment and the probability of something happening based on that experiment. So there's something called the law of large numbers, which is quite important. I know it's a very silly sounding name for such an important law. But it basically says that over time, as the number of experiments conducted increases, we've got that the empirical probability approaches the theoretical or classical probability. So think of it this way. If your experiment, in this case, if our experiment is flipping a coin, well, we could think of that theoretically, and then we could also do it in practice, and that would be its empirical probability. You probably realize that, the probability of flipping a coin, say, what's the probability of getting tails? Well, it's 50%. And you probably know that intrinsically, but why is it 50%? Of course, because it's favorable over total, right? If you're flipping a coin, the sample space is heads, tails. So that's 2. So our denominator is 2. And how many of those outcomes are favorable to us getting tails? Well, only 1. So it becomes 1 over 2, which is 50%, right? That's where that 50% theoretical probability comes from. But if you flip a coin in practice, say you flip it 10 times, it's not guaranteed to be half and half, right? You might get 6 tails and 4 heads, 7 tails, 3 heads. You might get 5 tails, 5 heads, but it's certainly not guaranteed. But as the number of experiments increases, so let's say you don't flip it 10 times, but 20 times, 50 times, 100 times, 1,000 times, the odds that the empirical probability is far away from the theoretical probability is extremely, extremely low. The more times you repeat the experiment, say when it was 10 times, we got tails 60% of the time. But when we did it 50 times, it was 53% of the time. When we did it 100 times, it was 50.5% of the time, right? They always keep tending towards that 50% because that's what the theoretical probability would be in that case. And that's what the law of large numbers is telling us. And that should conclude the review for 4.1. Okay, so section 4.2 is on the addition rules for probability. Really only need one formula. Which says that the probability of A or B happening is equal to the probability of A happening plus the probability of B happening minus the probability of A and B happening at the same time. So the idea behind this, I think it's helpful to look at a Venn diagram. Here's A, here's B. Right, the reason the formula is this way, we're looking to count this. Anything in A or B. But in the formula, you see here we do probability of A, which is all of this circle. And then we do probability of B, which is all of this circle. And if you'll notice, that means we're counting that middle part twice. That intersection. And that's what the subtraction does at the end, is it accounts for us counting that twice. It takes one of them away and gives us the proper number there in the probability. So that's kind of the idea behind this formula. When the events are what's called not mutually exclusive, when they are mutually exclusive, then the intersection will basically be 0, but the formula still works. So you don't need to memorize like 2 different formulas. You could just use this one. So let's look at some examples. A single card is drawn from a deck. What is the probability of getting a 9 or a diamond? Okay, so let me pull up that deck of cards again so we have it available to us to see. And this is a question where we've got to use the addition law. And the really key word is that it's the or. Right, we're looking for the probability of something or something else happening. And in that case, that's when we use the addition rule, or addition law, which I just mentioned to you guys, is the probability of A or B happening is the probability of A plus the probability of B minus the probability of A and B at the same time. So let's just translate it accordingly for this problem. What are we looking for here? Probability of getting a 9 or a diamond. That's kind of our event A and our event B. And so what's this going to be according to the formula? It's the probability of getting a 9 plus the probability of getting a diamond minus the probability of getting a 9 and a diamond at the same time. And then we evaluate these individually, add them up to get our answer of getting the probability of getting a 9 or a diamond. So what's our probability of getting a 9? Remember, favorable over total. Well, there's 4 9s, so that's our numerator out of 52 cards. That's our denominator. We also find the probability of getting a diamond. What's the probability of getting a diamond? Remember, favorable over total. If we're drawing one card, how many outcomes are favorable to us getting a diamond? Well, if you count that bottom row, that's the diamonds, there's 13 of them. That's our numerator. Out of the same total, 52 cards. But we may have counted certain things twice. And in fact, we've counted the 9 of diamonds twice. And that's what we end up subtracting away here. The probability of getting a 9 and diamond at the same time. Well, what's the probability of getting a 9 and diamond at the same time? Well, there's only one card that fits that description, the 9 of diamonds. So there's only one favorable outcome for that occurring. So we end up getting 1 for our numerator out of 52. The probability of getting a 9 of diamonds is 1 out of 52. This when we do this addition, let's see, 17 minus 1 gives us 16 out of 52. And that would be our answer. What's that reduced to? 8 over 26, 4 over 13. That would be the probability as a fraction, which is fine. You can leave it as a fraction or put it as a decimal or a percentage, I guess. Okay, let's look at maybe one more. And again, if the events are mutually exclusive, this is just going to be 0, but it's still fine that the formula still works. Anyway. In a hospital unit, there are 8 nurses and 5 physicians. In hospital unit, there are 8 nurses and 5 physicians. 7 nurses and 3 physicians are female. If a staff person is selected at random, find the probability that the subject is a nurse or a male. Again, we know to use this OR formula because it's saying find the probability that the subject is a nurse or a male. The OR is a keyword to use this additive probability formula. Probability of A or B is equal to probability of A plus probability of B minus probability of A and B at the same time. And the A and B in this case are going to be nurse and male. So we're looking for the probability that a random person selected is a nurse or a male. So that's probability of nurse plus probability of male minus the probability of nurse and male, a male nurse. So what's our probability that a randomly select person as a nurse? Let's see. Well, there's 8 nurses and 5 physicians. So that's a total of 13 employees, I guess I'll say. 8 of which are nurses. So our numerator is 8, and our denominator is 13. So that one's 8 out of 13. What's the probability that a randomly selected person is male? You kind of have to find this out indirectly, I guess. 7 nurses and 3 physicians are female. So since there's only 3 people left out of the 13, right? So 10 are female of the 13. That means 3 must be male. So the probability of getting a male is 3 out of 13. Minus the probability of getting a male nurse, which is what? Well, there's 7 nurses. No, 7 of the nurses are female, and there's 8 nurses. So there's only 1 male nurse. So that's minus 1 out of 13, giving us 9 out of 13 for this one. So not so bad as long as you can evaluate like the individual probability formulas, because this formula is pretty straightforward. It's just one formula, not too hard to remember either, I think. Okay, so next, a brief review of 4.3, which is on the multiplication rule. And conditional probability. So the multiplication rule says that when 2 events are independent, I'll write it this way. When 2 events A and B are independent, the probability of both occurring is, and so this is essentially telling us how to do probability of A and B. In the last section, we talked about A or B. Here, we're talking about A and B. Probability of A and B. And in this case, it's just the probability of A times the probability of B, which is relatively easy to remember, thankfully. And so what it means to be independent, it means that event A does not affect, if A occurs, it doesn't affect the probability of B occurring in any way. So, for example, if we say, what is the probability of rolling a 3 on a die and picking tails when flipping a coin? Or I guess I should say getting tails. Well, here we've got to use our first of all, they are independent from each other, right? Whether we get, it doesn't matter what we get on the dice. That's not going to influence our flip of the coin at all. So they are independent. So it's just the probability of A and B, right? Because we've got this keyword of and, probably getting a 3 on a die and getting tails when flipping a coin. It's probability of A and B. Well, they are independent, so it's probability of A times probability of B. Well, the probability of A, in this case, A is going to be the probability of rolling a 3 on a die. And what's that? Well, there's one outcome favorable out of 6, right? There's only one way to get a 3, just by rolling a 3 out of the total of 6 sides on the die, times the probability of B, and in this case, I'll let B represent getting tails when flipping a coin. The probability of that is 1/2, of course, giving us 1/12. Okay, and we've also got conditional probability. That's kind of when they aren't independent of each other. You know, event A happening influences the probability of B happening, or vice versa, something like that. So that's what's called conditional probability. And the formula for this, it says when two events A and B are dependent, the probability of both occurring is, so this formula is a bit tougher. It does have some weird notation. Its probability of A and B is equal to the probability of A times the probability of B given A. That's how we say this, basically. Probability of B occurring given or assuming A has occurred. And we say it the probability of B given A. So since A happens, the probability of B is affected, so we have to kind of take that into account. That's basically what this is saying. So let's look at an example. 3 cards are drawn from a deck and not replaced. Find the probability of so let's ask a couple of things. How about getting 3 jacks getting an ace, king, and queen in that order? And how about getting 3 clubs? And I'll get the picture again. Oops. Okay, so the probability of 3 jacks, that's kind of like jack and jack and jack, which is why we're using the conditional probability formula here. So the probability of getting 3 jacks, it's the probability that we get a jack times the probability that we get another jack. So probability of jack given jack times probability of jack given we've already got 2 jacks. Oops, sorry. So I'm basically just using the formula here. After we pick the first jack, the deck is different. It's got one less jack in there. And so the probability is going to be different. And you've got to account for that in the second and third pulls, essentially. So before anything happens, what's our probability of getting a jack? Well, favorable over total. There's 4 jacks out of 52 cards. So that one's just 4 out of 52. But now that we've picked one of the jacks, we don't know which one it is. It's arbitrary, but one of them is gone. So now, what's our numerator? How many outcomes are favorable to us getting another jack? Well, now there's only 3 left, so that's actually 3 here instead. The probability of another jack, given that our first card was a jack, is 3 out of 52. 51 rather, 51. The denominator also changes because the total, right? If we remove a jack, the total changes as well. It goes from 52 to 51. And then we times it again by the probability of getting another jack, given that 2 jacks are gone. Well, now there would be only 2 left and only 50 cards total left. So it'd be times 2 out of 50. So this is pretty tough. This idea definitely gets really hard to wrap your head around sometimes, or at first, I should say. And the notation could be confusing as well. So what do we get here? 4 times 3 times 2, it's 24 out of 52 times 51 times 50, which is 132,600. And I guess whatever this fraction reduces to, or decimal, we'll figure out what it is as a decimal. So it says here 1.8099999 or 1.809954751 e to the negative 4. That just means move the decimal 4 spots to the left. So if I move the decimal 4 spots to the left here, it'd be 0.000180995, blah, 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 however many decimals you want to write. So what is it again? 0.000 180,995. Like, it'll say however many decimals to go, but it's a really small number. So when the number is really that small, you kind of want more decimals of accuracy. So let's look at B. It's the probability of getting an ace, then a king, then a queen in that order. So before anything happens, right, we've got 52 cards. Probability of getting an ace. There's 4 aces out of 52 cards. Then we multiply this times the probability of getting a king given that we've picked an ace. That's what this notation means. The probability of getting a king given that we've already gotten an ace on our first pick. And so how many kings are there? Well, there's 4 kings. And how many total cards are there? Well, remember we lost an ace, so we lost 1 total card out of 52. So there's 51 left. And then the last one, probability, we multiply it times the probability of getting a queen, given that we've already gotten an ace and a king. And there's 4 queens and 50 total cards after that happens. And then we just multiply this together to get our answer. It's 64 divided by 132,600. That's 0.0004825, right? Again, we move the decimal 4 spots to the left. Gives us 0.0004825. 8 to 7. Part C, getting 3 clubs. And so, again, it's the probability of getting a club times the probability of getting another club, so club given club, and then times probability of getting another club given that we've already gotten 2 clubs. So the probability of getting a club is 13 out of 52. And then if we've already taken a club away, instead of 13, there's now 12 left, so that's 12 out of 52. And then after we've taken 2 away, there's 11 left, so that's times, 51 here. Messing up myself. And then the probability that we get another club, given we've already picked 2 clubs, there were 13, now there's 11, and there were 52 total cards, now there's 50. And then we just do this multiplication. So 13 times 12 times 11 divided by 52 times 51 times 50. It's 0.0129. 4. Which is higher than the other two. Looks like they're actually going in order of least likely to most likely in this question. Okay, another thing I want to mention is whenever we see the phrase at least. That's another keyword. So we've got a lot of keywords here to let us know which formulas to use. Remember, when it's or, we use the additive formula. Probability of A or B is probability of A plus probability of B minus probability of A and B. When they are not mutually exclusive, to find the probability of 2 events happening at the same time, so probability of A and B, there's 2 formulas, and it depends on whether they're independent of each other or not. If they're independent of each other, it's just probability of A times probability of B. If they're not, it's probability of A times probability of B given A. And now we see another key phrase of at least. And when you see the key phrase of at least, you want to use, it's called a complement formula. It involves complements. But I could use the word not as well. And so the phrase is probability of at least some number of A, essentially. And this is equal to 1 minus the probability of not getting A. So it's essentially like this. Something can either happen or not happen. And when you add those together, you get 100% of the outcomes. The 1 is basically 100%, and they basically just move the probability of what you don't want to the other side. So probability of what you do want, I could even write it out in words, of what you want is equal to 1 minus the probability of what you don't want. That's kind of, in words, what this formula is saying. And again, you want to use this when you see the key phrase of at least. So for example, a single die is rolled 4 times. Find the probability of getting at least 1/6. So we see the key phrase of at least. That again lets us know we want to use this complement principal formula for probability. And so what are we doing here? What are we looking for? The probability of getting at least 1/6. So I'll write here the probability of at least 1/6, and it's going to be equal to 1 minus the opposite of this. And what's the opposite of at least 1/6? Well, at least 1 means 1 or more. And what's the opposite of 1 or more? It's none. So it actually ends up being 1 minus the probability of getting no 6s. And in general, that's always the opposite of at least 1 is none, right? The opposite of at least 2 would be 1 or none. But in this class, I believe they only do at least 1. So it's just always going to be the opposite of at least 1 is none. And then that allows you to use the formula. So our probability of getting at least 1/6 is 1 minus the probability of getting no 6s. Well, think of it this way. We roll a die. What's our probability of not getting a 6? Well, our probability of getting a 6 is 1/6. Our probability of not getting a 6 is 5/6, right? Because there's 5 outcomes favorable to it not being a 6, a 1, a 2, a 3, a 4, or a 5, and there's 6 total options. So the probability that the first one is not a 6 is 5/6. The probability that the second one is not a 6 is 5/6. You multiply this together 4 times in accordance with the multiplication rule, right? It's basically not a 6 and not a 6 and not a 6 and not a 6. But they're independent of each other, so we could just multiply those probabilities together, giving us 1 minus, that's 5 to the 4 over 6 to the 4. 5 to the 4 is 625. 6 to the 4 is 1296. 625 over 1296. Sorry, I meant to put the 625 over 1296 here. We end up getting approximately 0.4823%. Oh, sorry, I didn't do the 1 minus. 1 minus that. I knew something was wrong. 1 minus 0.4823. 0.5177. And that would be our probability of getting at least 1/6. So again, you want to use this formula when you see the key phrase of at least 1. You know, it's always going to be at least 1 for this class. And the probability of at least one of something happening is 1 minus the probability that that thing never happens, that none of those things happen. And this is the formula in action here. Okay, so let's go ahead and move on to 4.4. which is on counting rules. And okay, so in a sequence of events, the total number of possibilities in the sequence is k1 times k2 times k3 times all the way down to kn, where n is the number of events in the sequence, and k with a subscript is the probability, or I'm sorry, the number of possibilities for that event. So it's just the number of ways to fulfill the first event times the number of ways to fulfill the second event, on and on and on until you fulfill all the events. So say you want to, for example, how about if a license plate has 3 digits followed by 3 letters, how many such license plates are possible? That's why these are called counting rules, because we're trying to count the number of ways that something can happen. Okay, so we want to use the fundamental counting principle here because we're allowed to repeat elements. For example, we could use a 3, and then another 3, or 5 for the first 3 digits. Or we could do ZZZ for the last 3 numbers, right? Letters, rather. We'll talk about what to do when repetitions are not allowed after this. But when repetitions are allowed, you can use the fundamental counting principle as we've got here. So in this case, right, a license plate, it's 3 digits and 3 letters, so that's 6 slots. So with the fundamental counting principle, you kind of just want to write out the number of slots for each event. In this case, an event being each digit or number, digit or letter. And then you write the number of possible outcomes for each event and multiply them all together. So, right, these 3 have to be a digit. So how many possible outcomes are there for these ones? Well, they could either be a 0, a 1, a 2, a 3, a 4, a 5, 6, 7, 8, or 9, which there are 10 of, right? Sorry, I was scrolled up down a bit too far. Right, these 3 slots, it says they need to be a digit. So how many possible outcomes are there for each event? 10. 10 for the first, 10 for the second, 10 for the third, because we're allowed to repeat the same digit over and over again. It doesn't say anything about repetitions not being allowed. And then the last 3 slots have to be a letter, which there are 26 of, right? A, B, C, all the way down to X, Y, and Z. There's 26 letters. So we've got 26 options for the first letter, 26 options for the second letter, 26 for the third letter. If repetitions aren't allowed, that would be, that would mean that whatever you pick in the first slot changes what you could put in the second slot. So it's similar to that conditional probability that we just spoke about, where if we weren't allowed to repeat digits or letters, it would be 10 in the first slot, then 9, and then 8. Because in the second slot, we can't use whatever digit we used in the first slot, so instead of having 10 to choose from, we've got 9. And then the third slot, instead of 10 to choose from, we have 8 to choose from. If we also weren't allowed to repeat letters, it would be 26 times 25 times 24. So being allowed to repeat and not being allowed to repeat is pretty important. You've got to realize if that's happening or not. And if you are allowed to repeat, you can use this fundamental counting principle. So I'll write here the fundamental counting principle, which is what we just spoke about, can be used when repetitions are allowed. When repetitions are not allowed, we use what are called permutations or combinations. And that's what we'll talk about here. So permutations are used to arrange n objects in a specific order. And that's a keyword, arrangement, that lets you know you want to use permutation. An arrangement of n objects in a specific order. So, and I should say, and again, it's an arrangement. So that in that word implies that you're not allowed to repeat, right? So say you've got like 5 children and you want to see how many ways you could line them up. Well, you can't repeat a child, right? You can only use that person once in one slot. And so you can't repeat, basically, is what I was trying to say. And also, in this case, we're going to say that order matters. And the formula for this is NPR is equal to n factorial over n minus r factorial. And of course, you've got to know what factorial is. And factorial basically just, well, the definition is it's the number times 1 minus that number times 2 minus that number all the way down to 1. And R is the group size. So there is probably a formula. If you've got a calculator, you've probably got a formula for this in here. So let's look at an example. A radio show host has 10 guests to choose from. A radio show host has 10 guests to choose from and needs to pick 3, and the order matters. We're going to assume that the order matters in this case. So, maybe the first person gets 15 minutes, the second person gets 10 minutes, the third person gets 5 minutes. So, something like that, in which case you want their order to matter. Well, if you've got 10 people to choose from, and you want to see how many ways we could select 3 of them where the order matters, it's going to be a permutation 10p3. The bigger number is always on the left. That's our n. The total number of things to choose from. And the number on the right is the group size that we're choosing. And a permutation, remember the order matters. Let's just do this one manually, might as well. So 10p3, according to the formula, that would be 10 factorial over 10 minus 3 in parentheses factorial, which is 10 factorial over 7 factorial. So we could do a lot of simplification here. What's 10 factorial? It's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. All of these ones are going to cancel, and we're actually just left with 10 times 9 times 8, which is 720. And that would be the number of different ways that we could select 3 people out of 10 where the order matters. On the calculator here, to do it here in this one, I would do, what am I looking for? 10p3, so it'd be 10. And I'd go to the permutation button and hit 3, so it looks like 10 NPR3. Hit enter, and it should give me that 720. As you see, it does. Okay, and a combination, we also cannot repeat, but in this case, the order does not matter. So the formula is NCR is equal to n factorial over r factorial times n minus r factorial. And we want to use this one when order does not matter. So let's say a committee of 12 people wants to make a subcommittee of 3 people. How many ways could they do this? Well, in this case, again, we can't repeat. It's not like Bob can serve twice on a committee of 3 people and count for 2 people. So we can't repeat, and we're saying it's just a subcommittee of 3 people. So it doesn't matter how you jumble them up, there's still that same subcommittee. And so we're assuming here that order does not matter. So in this case, we would want to use the combination formula. It would be 12C3. And 12C3, I guess I'll also do it manually just so you see a little bit more of practice of that. It's 12 factorial over 3 factorial times 9 factorial. If I write both of these out according to the definition, what do I get? 12 times 11 times 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. I've got 3 factorial, that's 3 times 2 times 1. I've got 9 factorial, 9 times 8, 7, 6, 5, 4, 3, 2, 1. Again, there's a bunch of cancellation. 9 all the way down to get us 12 times 11 times 10 over 3 times 2 times 1, which is 6. What's 12 times 11 times 10? 1320. Get 1320 divided by 6, which is 220. And that would be the number of different subcommittees that they can make, where they've got 12 people to choose from, and the subcommittee is 3 people, and the order of them doesn't matter. So I always teach my students a little flow chart of how to decide which of these formulas to use. You have to ask yourself 2 questions. The first question you ask yourself is, are repetitions allowed? If yes, we just can use the fundamental counting principle. If no, we've got to ask ourselves a second question, which is, does order matter or not? If the order that you put them in matters, we've got to use the permutation formula and PR. If the order does not matter, we use combination formula, which is NCR. So this is like a decision flow chart for how to decide which formula to use, because it could be quite confusing for sure. Okay, and then the last section here in chapter 4, which is very difficult, very long section. Definitely make sure to be really studious about this one before you take the quiz, because it's quite difficult stuff here. 4.5 is basically a mix of the rules that we've learned, the probability rules and the counting rules. So basically this section just gives some really tough questions. There's some really tough questions in this one, where they're mixing all the rules. It could become pretty complicated. But they mostly just do examples. There's no new stuff. It's just a combination of all the stuff we've learned. So they mostly just ramp up the difficulty of the questions. So let's just go ahead and do a bunch of examples together. Okay, so this question says, find the probability of getting 4 aces when 5 cards are drawn from a standard deck. So a lot of these questions are about keywords, identifying keywords in the problem so that you know which formulas to use. First of all, we've got the keyword probability. And what do we know for probability? It's favorable over total, and it's a fraction. So now we know we can basically set it up as a fraction where the numerator is the number of favorable outcomes and the denominator is the number of unfavorable outcomes. And what are we looking for? The probability of getting 4 aces when 5 cards are drawn from a standard deck. So I'll say here probability of 4 aces. And as I mentioned, it's probability, so it's got to be a fraction. So putting numerator and denominator here. And so think about it. We're drawing 5 cards. The denominator is sometimes easier to find first. If we're drawing 5 cards, think about that. First, you ask yourself, are repetitions allowed? Remember, that's our flow chart questions to ask. Are repetitions allowed? No, you're drawing 5 different cards. And so since repetitions are not allowed, it's either got to be a combination or a permutation. And we're looking for 4 aces when we're drawing 5 cards. So what's our total number of outcomes? That's our denominator. If we're drawing 5 cards, how many different outcomes are there? Well, again, we're not allowed to repeat. And does the order matter or not? Well, it's essentially talking about a poker hand. And in this case, if you've got 5 cards in your hand, it doesn't matter which order you present them in. You could even jumble them up. It doesn't change your hand strength, actually. So whenever it's talking about drawing 5 cards from a deck, or a poker hand or anything like that, it's using combinations. It's assuming that the order does not matter. I know a straight, right? You've got to have 5 cards in the same in the same order, but you could have 6, 3, 2, 5, 4, and it's still a straight. They don't need to actually be in that order. So it's actually a combination. So it's a combination, and how many things do we have to choose from? Well, there's 52 cards, and how many are we choosing? 5. So our denominator is 52 choose 5. That's another way of saying it, 52 choose 5. And our numerator, the number of favorable outcomes to getting 4 aces. Well, again, order doesn't matter, and we can't repeat, so it's a combination. And how many aces do we have to choose from? 4. And how many do we need? Well, we need all 4. And then we've got one more card to pick. And how many are left? If we've picked 4 already, there's 48 left. So it would be times 48. But definitely a very, very tough question. So 4C4, that's actually 1. Anything C itself is just 1. So it's actually just 1 times 48 over whatever 52C5 is, which is 2,598,960. So obviously it's a very small probability, but what's this fraction going to be? 48 out of that number. It's 0.00001847. Remember, we moved the decimal this time 5 spots to the left, which would mean we would have a decimal and then 4 zeros. But definitely a very tough question. Let's look at some more. A box containing circuits contains 4 of which are defective. If 4 are sold at random, oh, I forgot the number. I didn't write the number. It contains 24 circuits, 4 of which are defective. If 4 are sold at random, find the following probabilities. And we've got here A, that exactly 2 are defective. That's our first one. Let's look at that. Again, it's a probability, so we know it's got to be a fraction. What are we looking for? The probability that we've got 2 defective. And we know it's a fraction. Let's figure out our denominator first. Again, that's usually the easier one. And let's think. We can't repeat. We're picking different circuits. We can't just pick the same one over and over. And I think that we can say that the order doesn't matter. You just jumble them up. It's the same thing. So it's going to be a combination. We've got 24 to choose from, and we're choosing 4. Right? 4 are being sold at random. So that's 24C4. The numerator is going to be the number of ways that we could have exactly 2 of them being defective. So we want 2 to be defective, and there's 4 that are defective. And the order doesn't matter, so that's 4C2. But we've only chosen 2. We've got to choose 2 more. And we want to choose it from the non-defective ones because we want to make sure we're getting exactly 2. We've already made sure we've got exactly 2. So if there's 24 circuits total, that means there's 20 that are not defective, and we're also choosing 2 of those. Multiplying these together, doing all this math, we get 1140 over 10,626, which is 190 over 1771, which you could also get as a decimal. Let's look at some more. What about the probability that none are defective? Well, our denominator is going to stay the same. There's 24 to choose, right? The total number of outcomes. Well, there's 24 to choose from, and we're choosing 4 at random. So that's the total possible number of outcomes. And in this case, what's our numerator going to be? We want to make sure that none of them are defective. So we've got to choose only from non-defective ones. If there's 24 circuits, 4 of which are defective, that would mean 20 are not defective, and we're also choosing 4 still. So it'd be 20 choose 4 over 24 choose 4, which is 1650, reduces, well, I'll write out first what it is. 4,845 over 10,626, which is 1,615 over 3,542. How about the probability that at least 1 is defective? Well, remember, we've got that keyword there of at least 1. And in that case, we could use our complement principle, which is the probability of the event happening is 1 minus the probability of the event not happening. We're looking for the probability that we've got at least 1 defective. And in this case, our denominator is still the same. We've got 24 to choose from. We're choosing 4. Oh, sorry, I didn't do the formula. It's 1 minus the probability that none are defective. right? This is the complement formula that we discussed earlier. The probability of something that you want is 1 minus the probability of the thing that you don't want. It's like the opposite. And you want to use that when we see the phrase at least 1. So we'll get 1, it's 1 minus the probability that none are defective. And we actually found that just now. Remember, it was 20C4 over 24C4. Which ends up being 1927 over 3542. Okay, so these questions are definitely really, really tough. Probability itself is really hard, and then you've got to combine all these rules together at one time. It can certainly be a lot. So don't get too discouraged if you're not getting all this material or you don't do fantastic on this quiz, because this is probably some of the hardest material in the whole course. So thanks for listening to this review. I hope it helps. Please email me if you have any questions, anything like that. Thanks for watching, and I'll see you in the next one.